We noted in the previous video that the rates of many chemical reactions depend on the concentration of reactants. In this video, we look at the relationship between reactant concentration and time in more detail, and we introduce the concept of integrated rate laws. If we consider the simplest form of a generalized chemical reaction in which a single reactant A is converted to a single product B, we can write the generalized form of a rate law like this, where the rate equals the rate constant K times the concentration of A raised to the power m, where the exponent m represents the order of reaction with respect to A. If this reaction happens to be a first order reaction, then the value of the exponent m is equal to 1. And the rate law is the rate equals K times the concentration of A. If the reaction happens to be a second order reaction, then the value of the exponent m is equal to 2, and the rate law is rate equals K times the concentration of A squared. And if the reaction happens to be a zero order reaction, then the value of the exponent m is equal to 0, and the rate law is rate equals K times the concentration of A to the power of 0, which equals 1, and so the rate simplifies to being rate equals K. What rate laws show is how the rate of reaction is related to the concentration of reactants, and whilst this is very important in many industrial, environmental, and biomedical applications, it is also just as important to be able to predict the concentration of a reactant or product at any time during a chemical reaction. An integrated rate law will allow this. An integrated rate law is a relationship that expresses the concentration of a reactant as a function of time as the reaction proceeds. Now, this reaction of A going to B implies that as the reaction proceeds, A is being consumed and B is being produced. And we can plot the course of this reaction using a concentration time plot where we see that as A is consumed, its concentration decreases with time, and as B is produced, its concentration increases with time. Now, you may recall from an earlier video that the rate of reaction for this reaction can be determined from the slope of these curves at any point during the reaction, and this is known as the instantaneous rate, and is determined by calculating the slope of the tangent by considering the change in concentration of a reactant or product divided by the change in time. So the instantaneous rate at any time during the reaction can be expressed as minus the change in concentration of A divided by the change in time. And remember, the negative sign is there because we are talking about the rate of disappearance of a reactant, and we need to ensure we have a positive value for the rate of reaction. So what we have now are two ways of expressing the rate, and both expressions are equally valid ways of expressing the rate of this reaction. And because these two expressions are both equal to the rate of reaction, we can equate the terms on the right-hand side to give this expression here. Now, we have already established that if this reaction happens to be first order with respect to A, then the right-hand side of this expression will equal K times the concentration of A. If the reaction happens to be second order with respect to A, then the right-hand side of this expression will be K times the concentration of A squared. And if the reaction happens to be zero order with respect to A, then the right-hand side of this expression will just be the rate constant. So what we'll do is now consider all three of these cases, one at a time, starting with the first order case, where the right-hand side of the equation is equal to the rate constant K times the concentration of A raised to the power of 1, which does not need to be written. We can rearrange this equation and do a little calculus involving integration of the function within limits to achieve this relationship here, which is known as the first order integrated rate law. Now, while the derivation of this expression is not too complicated, in chemistry the ability to understand and apply this equation is far more important than knowledge of its mathematical derivation. Consequently, it is important to understand exactly what each term means, with the concentration of AT term referring to the concentration of the reactant A at any time t during the reaction, and it has the unit of molarity. The concentration of A0 term refers to the initial concentration of the reactant A at the start of the reaction, that is at time t equals 0, with the unit again being molarity. K refers to the first order rate constant with the units of seconds to the minus 1. And finally, T refers to the time interval of the reaction with the unit being seconds. So what we have is a relationship that relates the concentration of a reactant to the time of the reaction. The overall equation actually reads as the natural log of the concentration of reactant A at any time during the reaction is equal to minus Kt plus the natural log of the initial reactant concentration. And this means we should be able to calculate the concentration of reactant at any time during a reaction so long as we know certain other key experimental factors, such as the time of the reaction, the value of the rate constant K, and the initial concentration of the reactant. It turns out that this equation has the general form of a straight line, y equals mx plus b, where in the case of our integrated rate law, the ln term is equivalent to the y variable, the time variable is equivalent to the x variable, the negative of the rate constant minus k is equivalent to the slope of the straight line, and the natural log of the initial concentration is equivalent to the y-intercept. And so while we see that for a first order rate process the concentration of the reactant A will decrease exponentially with time, if we were to plot the natural log of the concentration versus time, we would see a straight line relationship with a slope equal to minus k and a y-intercept equal to the log of the initial concentration of A. And we'll see in the next video how this information becomes very valuable in trying to determine things like the order of reaction as well as calculating the rate constant of chemical reactions. A slightly rearranged form of the first order rate law, where the equation is expressed in terms of the ratio of starting concentration and final concentration, will often be useful. However, both forms of this integrated rate law equation can be used to do some very useful calculations. For example, if we know the initial concentration of a reactant, and if we know its final concentration after a time period t, then the only unknown in this equation is the rate constant K, which can be readily calculated. If, on the other hand, we know the rate constant K, and we know the initial concentration of the reactant that we start with, and if we wanted to reduce this concentration to a certain known value, then we can readily calculate the time period it would take to go from one concentration value to another. For a second order reaction, the rate of reaction is proportional to the concentration of the reactant squared, and so the right hand side of this equation becomes K times the concentration of A squared. Again, we can rearrange this equation and do a little calculus involving integration to achieve this relationship here, which is known as the second order integrated rate law equation. Again, in chemistry, the mathematical derivation of this expression is less important than the ability to understand and apply this equation. The terms in this equation have the same meaning as previously, except that the rate constant K in this case is known as the second order rate constant and has the units molarity to the -1, seconds to the -1, or litres per mole per second. Like the first order rate equation, the second order integrated rate equation also takes the form of a straight line equation, where the 1 over AT term is equivalent to the y variable, time is again equivalent to the x variable, the rate constant is equivalent to the slope of the straight line, and the 1 over A0 term is equivalent to the y-intercept. In a second order reaction, the concentration of reactant will decrease in an exponential-like manner similar to the first order case, but the biggest difference is that the decay towards zero is slower in the second order case. Nevertheless, if instead of plotting concentration versus time, we were to plot 1 over the reactant concentration versus time, in accordance with the second order rate equation on the left, we would see a straight line relationship with a positive slope that has a magnitude equal to the value of the rate constant K. In this case, the y-intercept would be equal to 1 over the starting concentration of A. For a zero-order reaction, the rate of reaction is constant, and so the right-hand side of this equation simply becomes the rate constant K. Again, we can rearrange this equation and do a little calculus involving integration to achieve this relationship here, which is known as the zeroth order integrated rate law equation. The terms in this equation have the same meaning as previous, except that the rate constant K in this case is known as the zeroth order rate constant and has the units molarity per second or moles per litre per second. Like in the previous cases, the zeroth order integrated rate equation also takes the form of a straight line equation, where the AT term is equivalent to the y variable, time is again equivalent to the x variable, The negative of the rate constant k is equivalent to the slope of the straight line, and the A0 term is equivalent to the y-intercept. In a zero-order reaction, the concentration of reactant will decrease linearly with respect to time, which is quite different to the other cases. And this linear decrease is consistent with a rate of reaction that is constant. So in this case, the plot of the reactant concentration versus time is actually the defining plot to look at, and we see that the slope of this line will be equal to minus k, and the y-intercept equals the starting concentration of A. This table here summarizes all of the important relationships for integrated rate laws, which relate the concentration of a reactant to time during the course of a reaction. The table considers the case for the reactants that conform to 0, first, and second order rate kinetics, and shows the equations for the rate law in each case. It shows the units for the rate constant in each case. It shows the integrated rate law equation in each case. And it shows the information for the straight line graphs in each case, which allow us to determine which variables to plot against which other variables in each case. The table also refers to mathematical expressions for the half-life of chemical reactions, which we will consider in more detail in a subsequent video. However, the next video in this series shows us how we can use the integrated rate laws in a very practical way to perform calculations to predict key experimental parameters, such as determining the rate law equations, determining the values of the rate constant, as well as determining the concentration of a reactant at any time during a reaction, or determining the length of time a reaction will take to produce a certain amount of product.